The Gizeh Plateau near Cairo. Among its mysteries is a peculiar geometric anomaly. The sides of the Great Pyramid aren't exactly flat. During the equinox, they look slightly concave. Over time, this has led to many claims of an 8-sided pyramid. Does the Great Pyramid really have 8 sides? We'll first cover the background, photos, and theories. Then we'll give our 3D analysis. As always, we colorize and enhance old photos and illustrations. If you want to see more videos like this, subscribe and share. The first to describe the concavity on the sides of the Great Pyramid were the savants during Napoleon's expedition to Egypt in 1798. Jacques Grobert said that the center of each face had suffered more damage than the edges, and thus it's very dangerous to climb the pyramid that way. Edmé Jamard said that the cause of this were stones dislodged and falling from the upper parts of the pyramid. By the way, they use the geometric term apothegm, which is quite useful in this context. In geometry, an apothegm is a line connecting a vertex with the middle of the opposite face. In our context, it's this green line. The next key event in this story is this photo, clearly showing the concavity. It was taken by the British RAF pilot Percy Groves just before sunset from 4,000 feet. Let's clear up 2 things. 1. Some report the date of this photo as 1940, but it was published in National Geographic in 1926. 2. Groves had indeed been in the RAF, but he quit the service in 1922, and in 1926 he was flying a civilian plane. The goal of this article seems to be promotion of air travel when visiting the Middle East. This photo became well known among pyramid researchers. It led to several theories about why the pyramid has 8 sides, based on the assumption that this shape was intentional. While the concavity is real, photos showing it are sometimes altered to various degrees. The Groves photo is usually shown with more contrast to enhance this feature. In other cases, the manipulation is more stealthy. These 2 particular images have been adopted from satellite imagery. If we alternate between them and the satellite originals, we can see that the shading on the triangular halves of each side has been manipulated. Extracting the image difference with respect to the originals shows where the shadow areas have been altered. Now, a brief overview of theories which assume that the concavity was planned by the builders. Several theories claim some structural benefits to this 8-sided shape. One theory proposes that casing that's thicker in the middle would better bind the casing stones to the core masonry. The problem is that all pyramids said to have concavities have no limestone casing left today. But the one pyramid which is not said to have a concavity, Khafra, still has some casing left. In other words, the end results are 180 degrees opposite of what this theory postulates. Another structural theory posits that an 8-sided shape gives more stability, by analogy to how dams curve in the middle. Firstly, dams form an arc to redirect forces when they brace against something, like canyon walls or an embankment. Pyramids don't brace against anything. Secondly, an 8-sided shape is already contained within the equivalent square. Whatever benefit an 8-sided shape has, it's already included in a square. The only reason to not have these additional parts, in blue, would be to save material. Since the end goal is a square structure anyway, there's nothing to save, so the 8-sided benefits argument is moot. Another theory says that the concavity's purpose was to indicate the equinox, as the shadow flipped from one half to another. But the concavities also exist on the east and west faces, which makes no sense in terms of indicating the equinox. More importantly, all concavities were hidden from view when the pyramids still had their casing. We have remaining casing blocks on the Khufu and Red Pyramids, and the granite blocks on the Menkaure pyramid. They all form a straight line on the outside, refuting this theory. Today, the idea that the concavity was carved out entirely by damage is best expressed in a paper by Frank Monnier. As the pyramids were being stripped of their smooth casing, and later human activity, the exposed inner core was subject to damage from the blocks falling down. Since each face is an upright triangle, more stones tumbled down the center compared to the edges, so the damage is heavier in the center. In his paper, as a reference, Monnier uses data from a 3D scan of the Great Pyramid done in 2005 by an Austrian team. To verify the damage theory, Monnier shows the results of his simple statistical simulation made in Excel. It computes what happens when simulated blocks fall down the face from each cell, damaging the cells below. The resulting color map shows the damage accumulated over time. This damage pattern resembles the observed concavity. In general, we agree with Grobert and Monnier that the concavity was made by falling blocks, and we'll soon explain why. But there are physical aspects and pattern features of this concavity which haven't been previously discussed. Let's do this now. First, let's discuss physical behavior that Monnier's simple Excel calculation doesn't account for. As we understand it, for any cell, Monnier summed up the wear caused by each and every cell in the vertical column above. But being in continuous contact with the pyramid's face would probably occur only at the beginning of a block's fall. Subsequently, the blocks would likely develop bouncing behavior. To illustrate this, here are sample RBD simulations of a block released from the top of about 200 courses, like the Great Pyramid. As the block tumbles down, it bounces in progressively bigger leaps due to gravity. These simulations don't show real bouncing distances, as the coefficients aren't taken from experiments with real limestone blocks falling down a pyramid. But yes, large boulders can bounce surprisingly high. The key point here is that the depth map of the concavity isn't a simple summation of vertical columns. It's the statistical outcome of hundreds of thousands of impacts. And since many blocks would break too, this includes secondary impacts. Blocks falling down a pyramid don't always follow straight trajectories, as shown in this front view of the simulations. Due to the angular geometry, with each collision, the trajectory can be deflected. This can be seen with real angular boulders. For this reason, the resulting pattern is wider than in this simple Excel simulation. Accumulating damage from the entire vertical column above a cell would apply only in two cases. 1. The casing was dismantled starting at the bottom edge of each face. 2. The casing slid down all at once in one big, simultaneous event. On the other hand, if dismantling started at the top, the still present blocks below would protect the core masonry from damage. It seems unlikely that dismantling started at the bottom of each face. When you actually see a human being under hanging casing stones, dismantling casing blocks from the bottom sounds like a somewhat dangerous proposition. You could dismantle from the bottom once you get to a height when the blocks get smaller and manageable. Logistically, the most rational approach to organized dismantling would likely be to move up the ridges. Reason 1. The corners are the most vulnerable areas of any pyramid's casing. On the Great Pyramid, their corners were likely already damaged in many spots when organized dismantling started. Reason 2. The ridges are the safest route for workers to climb. To perform our 3D analysis, we needed 3D models of the Gizeh pyramids. We obtained them through the magic of photogrammetry. The models are very heavy, millions of polygons, so we constrained our analysis to 2 faces per pyramid. The models let us extract a depth map, which shows how deep the masonry we see today was under the original casing surface. Let's start with the Great Pyramid. To analyze the concavity, we first established 3D contour lines for each course. You can't analyze the overall shape of the concavity based on a single contour line, as the blocks introduce noise. But if we average out all contour lines, adjusting for length, we get this general underlying pattern, present in all courses of the Great Pyramid. This is the profile of the concavity separated from all noise from individual blocks. Note that it's scaled up in this direction for a clearer view. In reality, this distance is about 1 meter. Here's our verdict. This concavity is not intentional and not part of the original design. Had the pyramid been planned as 8-sided, we'd see a V profile made of straight lines. But the profile, in its general shape, is a bell curve. A bell curve is a telltale sign of random factors or behavior, like falling blocks in this case. But this profile is more complex than a single bell curve. To us, it looks like 3 overlaid bell curves, each an imprint of a separate stage of the damage process. Here's our interpretation of these features, starting from the edge and moving toward the center. The corner is obvious. The roundness is simply the average of all corner blocks making a turn. Corner blocks, whether casing or core masonry, are horizontally braced only on one side. This makes them more vulnerable than blocks in the middle of a face. Other than the corners, the profile of the concavity seems to consist of 3 components. The most basic of its component curves, in green, can be called primary face-wide damage, caused by blocks dislodged from anywhere on the pyramid's face. If this component were present by itself, without other components, the profile would likely look like this. This basic component is likely shallower than Monnier's face-wide simulation. Recall that this simulation shows what would happen if all casing blocks originally present contributed to the damage. To us, it's unlikely to be the case. It would require either a planned dismantling from the bottom or a simultaneous casing collapse on the whole pyramid. We think only a smaller random subset of all casing blocks contributed to this face-wide damage. Here's why. The casing damage was likely initiated by natural causes, earthquakes, erosion, etc. Thus, the original seeds of damage were isolated spots, either on the corners or in a few random locations on the faces, probably similar to what we see today on the Medum pyramid. Except in Medum, we see one of the inner cased layers, not the original outermost one. In other words, before people started harvesting the casing stones, the Great Pyramid may have looked something like this. Humans are very opportunistic. The first phase of harvesting the casing was thus likely done by individuals, exploiting and enlarging existing, naturally damaged spots. These individuals did not follow any larger plan or direction. They just got the blocks they wanted from randomly scattered spots and moved on. At this stage, if blocks tumbled down the face, most of it remained protected by the existing casing. The next stage was organized harvesting of casing stones. We don't know the exact timeline of this phase. We know the casing was stripped of the subsidiary pyramids in 1170s to make the Cairo Citadel and a bridge in Gizeh. According to travelers' reports, the Great Pyramid had lost all of its casing by the very end of the 15th century. What we know for sure is that in 1395, organized casing removal was taking place on the Great Pyramid. That's when the French nobleman Ogier visited Gizeh and noted the following. Halfway up the slope of the pyramid, masons were using tackle to remove pyramid blocks and let them fall down. The greater part of buildings in Cairo and Old Cairo, or Babylon, were made of these blocks and had been made for a long time. About half of the casing had been removed by that time. And here's the crucial line. The Sultan takes 2/3 of the profits, the masons keep 1/3. In other words, the casing removal operation was not just organized, but possibly state-sponsored. The buildings in Cairo that likely incorporate pyramid blocks are the Sultan Hassan Mosque and the Sultan Barkuk Mosque. Incidentally, Wayman Dixon and Dr. Grant, who both discovered the Queen's chamber shafts, climbed to the top of the Sultan Hassan Mosque to look for any recognizable pyramid stones, but they were chased away by the custodians. Perhaps under the foundations of these mosques, there's indeed still recognizable material from the pyramids, maybe even with inscriptions, but good luck getting a permit to excavate there. Returning to our analysis, this medium component, in blue, seems to be linked to the removal of volume from the top of the pyramid. On one face, this component is distinct enough to trace it back to its point of origin, which seems to be the top platform. The key point here is that the second component stands out from the primary component as a distinct, separate feature. Monnier's simulations correctly show that if the summit's volume were removed simultaneously with the casing, both at full amplitude, we'd get a smooth blended pattern with no distinction. But in our case, these two components are distinct. Recall that the primary face-wide damage likely occurred only at partial amplitude, because some of the face was still covered. The second component stands out because it occurred at full amplitude when the casing was already gone. In plain English, the stones from the summit were cast down after the removal of the casing. When, and in what stages, is a separate issue. In a previous video, we suggested that maybe the top plateau was modified for use as a military observation post during wartime. Since the casing removal ended roughly in 1500, some courses may have been removed before the Battle of Redania in 1517. The summit was enlarged again in 1798 during Napoleon's invasion of Egypt by one of the two sides. For more details, watch these two videos. Strangely, since 1800 there have been no further changes of any kind, all the way to the present day. This means that mass tourism, since 1860s onward, had surprisingly no impact on the summit. As far as we know, the earliest notice of the 1798 peculiarity is in one of Stefan Bergdahl's books. What about the narrowest third component? It's a channel, roughly 2 meters across, that runs down the apothem, or the center line of each face. It's this channel that gives the concavity a sharply defined edge. This creates a V-shaped appearance, even though the profile, in fact, is made of curves, not straight lines. The narrow channel in the middle could simply be a part of the second component, the bell of the bell curve. But there's something puzzling about it. These centerline channels remain unusually parallel down their whole length. This differs from the second component, which flares out towards the bottom in a triangular shape. Possibly, these centerline channels weren't driven purely by randomness, like the other components. They could be linked to some human activity, either as a byproduct or a deliberate creation. What's also somewhat unusual is that these channels are equal in width and depth on each side. If they were the result of vandalism, people toppling blocks for fun, the eastern channel would probably be more pronounced than others. Virtually all visitors through the ages have approached the pyramid from the east. Vandals who climb to the top would probably tend to push the blocks down the eastern or southern sides to show off for their companions on the ground. In contrast, the equal depth and width of the channels on all sides may hint at a more planned or practical purpose. Here's one possible explanation. Maybe during the organized casing removal, some kind of pathways leading up the center lines were carved for workers for easier access to the central areas of each face. Climbing up the apothem while the casing is in place is basically impossible, though an athletic, nimble person may be able to reach the top along the ridge. With the stepped inner masonry exposed, workers can climb up here, though they may still need the aid of ropes. The apothem channels give us a subtle hint as to when they first appeared. On the eastern and southern sides, they don't reach the ground, but on the other sides they do. This confirms that they were not part of the original design, else all of them would reach the ground. The likely reason is that when the channels appeared, there were piles of rubble under these sides. These piles come and go across the ages, their height and location changes. This pattern implies that the apothem channels appeared when there were rubble piles under the eastern and southern faces, but not the others. In the context of concavities, the Khafra pyramid has always been the odd one out. Monnier, in his paper, justifiably wonders why it doesn't have such concavities. We wondered about it ourselves, so we decided to apply our 3D analysis to this pyramid too. Here's the depth map and coarse contours. If we remove the block noise, it turns out that the rough section in fact does have an underlying concavity. It's actually about as deep as the one on the Great Pyramid. It's simply masked by the heavy roughness. But this applies only to the rough part. For the exposed core masonry, between the rough part and the casing cap, the profile is very straight. The lack of damage here is unusual. It implies only a very brief contact with any falling blocks. Perhaps in this section, the blocks fell off all at once in some short event. Maybe this discouraged casing removal above this level. As to why the backing stones are still preserved in the rough section, that's a separate issue. Maybe a different statistical distribution of vertical and horizontal block fractions, compared to the Great Pyramid, resulted in better bonding with core masonry. Like coffres, the bent pyramid is not associated with concavities either. But, in top views with the right angle and lighting, we can take an image strip across one face, squish it, enhance its contrast, then extract one component. We can then see that a shallow face-wide damage pattern is starting to form on the bent pyramid too. Note that the cause, human activity or natural deterioration, doesn't matter. Blocks falling down for any reason will over time begin to form this concavity. Let's sum it all up. Are the faces of the Great Pyramid concave? Yes. Does it have 8 sides? No, and it never had, inside or outside. The underlying general profile of the concavity is not a V-shape, as in the case of an intentional 8-sided design. Rather, it's one or more bell-like curves. Such curves are a telltale sign of many randomly driven events or factors. In this case, many rocks tumbling down and damaging the masonry. Which pyramids have concavities? Every pyramid that lost a big part of its casing has the primary face-wide component to some degree. This includes pyramids not previously associated with concavities, like coffres. The Great Pyramid has additional components, possibly the result of toppling down the volume from the summit. It also has narrow channels along its apothems. The parallel contours of these channels seem unnatural, possibly the result of some human intervention. Blocks falling down for any reason will over time form such concavities. Even if humans never touched the casing stones, over millennia the casing would deteriorate, and nature would carve slight concavities on its own.